Hi everybody, Ryan Jackson here. Thank you for joining me. We're going to be talking about feeder taps based on the 2020 National Electrical Code. And feeder taps is kind of a strange subject. You know, when we get into Article 240 and we talk about overcurrent protection, and that's already one of the more difficult things in the code, properly sizing circuit breakers and fuses to protect conductors. Uh, with a normal circuit, you got a bathroom, a 20 amp circuit, something like that, it's easy enough. Or even sometimes if you have a water heater or something like that, it's really not too terribly difficult. Once we start getting into motors, things start to get a little bit trickier. And once we get into feeder taps, if you're not familiar with them, they almost seem kind of voodoo. And because of that, a lot of people are afraid to ever use the feeder tap allowances because they don't understand them. And what I've found is once you understand the principles and why a feeder tap is allowed, you're much more likely to use the feeder tap allowances. And there's a lot of value in understanding where and when you can use a feeder tap. I'll tell you a story here in a little bit where a feeder tap really saved me a ton of work in the field. So we're going to base this on the 2020 NEC, but to be perfectly honest, nothing really changed as far as this is concerned. So 2017, if that's all you have, that's okay too. Before we get into it though, we need to understand what overcurrent is, because a feeder tap is providing overcurrent protection for conductors in an unusual manner. So we need to know what overcurrent protection is, and before we know what overcurrent protection is, we need to know what overcurrent is. Overcurrent is defined in Article 100 as current that exceeds the rating of equipment or the ampacity of a conductor. So two things here. I can exceed the rating of equipment, and that would be an overcurrent condition, or if I exceed the ampacity of a conductor, that also is overcurrent. Now, Article 240 only deals with the second part. Article 240 deals with protecting conductors. When it comes to protecting equipment, we go to the equipment article. So where would I find the rules for protecting transformers? You would go to Article 450. Where do you find the rules for protecting the conductors leaving the transformer? You would go to Article 240. So where do you find the rules for protecting a panel board? You go to 408.36, the panel board article. Where do you find the rules for the conductors supplying a panel board? You would go to 215.2, feeder circuits. So again, overcurrent is current that exceeds the rating of equipment or the ampacity of a conductor. Overcurrent can be from an overload, a ground fault, or a short circuit. Any one of those three creates an overcurrent condition. And overcurrent protection is protection against all three of those. If all you have is overload protection, you do not have overcurrent protection. You just have overload protection. If all you have is ground fault and short circuit protection, you do not have overcurrent protection. All you have is ground fault and short circuit. So overcurrent protection protects against overloads and ground faults and short circuits. So what are those three? Well, the first one is a ground fault, and a ground fault is an unintentional connection between an ungrounded conductor, a hot conductor, and normally non-current carrying metal parts or the earth. All right, so take a look at the picture here. Here we've got a metal faceplate. That would be a normally non-current carrying metal object, and it's collided with an ungrounded conductor, and that resulted in a ground fault. So on a ground fault, the thing to remember is that we have hundreds and probably thousands of amps of current flowing for a very brief time. Providing ground fault protection, and when I'm talking ground fault protection, I'm not talking about GFCIs and GFPE for today, okay? We're just talking about protection from this, taking a black wire and hitting it up against a metal object. So providing ground fault protection usually isn't too difficult because a ground fault creates thousands of amps of current, so tripping a circuit breaker is, or opening a fuse is very easy. We also have short circuits, and this is a phrase that's not defined in the NEC, and it probably should be. I think I've already submitted a proposal for the 2023 to define the term. But a short circuit is a connection between ungrounded conductors of different phases or lines, or between a grounded and ungrounded conductor. And again, that's not defined. That's just me talking here because it's not defined anywhere in the code. You take a black and a red wire, smack them together, that would be a short circuit. Take a blue and a white wire, hit them together, that would be a short circuit. Just like a ground fault, a short circuit pulls thousands of amps for a very brief duration, opens the overcurrent device. So ground faults and short circuits are both considered faults. And we always use the same device to protect against both types of faults, ground faults and short circuits. You really couldn't protect against one and not the other. So ground faults and short circuits, we have a fuse or a circuit breaker, hit the wires together, or take a black wire, hit it up against something metal, ground faults and short circuits. The other type of overcurrent condition we have to protect against is an overload. An overload is operation of equipment in excess of its rating. Okay, so if the equipment is pulling, because of some sort of malfunction, is pulling more current than what it's rated, that would be an overload. But today we're going to be talking about the second part, operation of a conductor in excess of its ampacity. So we need to provide overload protection for conductors, not just ground fault and short circuit protection, but overload as well. This conductor here in the photograph started its life as a brown conductor and has turned into a black conductor over time because it was subjected to currents well beyond its ampacity. So ground faults, short circuits, and overloads are what we have to protect against. The next definition that we're going to hit is in 240.2, and that's tap conductor, the reason that we're here. A tap conductor is a conductor other than a service conductor. Okay, let me just push pause right here. There's no such thing as tapping a service conductor because it simply doesn't jibe with the definition. It's like asking somebody, how warm do you jump? You know, it doesn't jibe, because a tap conductor is a conductor that has overcurrent protection at its supply that exceeds the rating that's normally allowed. Well, service conductors don't have overcurrent protection at their supply, so you couldn't possibly have a tapped service conductor. It's not possible. So here in the photograph, we've got some 1-aught conductor protected by a 150 amp circuit breaker. That's just a regular feeder, right? That just meets the regular feeder circuit rules. Coming out of this power distribution block, we have some 8 gauge that's going down to a 50 amp device. Now, that's either one of a couple of things. Either that's a normal circuit, and we know it's not, because a normal circuit, you can't put 8 gauge on a 150 amp breaker, so we know it's not a normal circuit, which means it has to be either a tap conductor or it's a violation. One of those two. You either have a normal circuit, or you have a tap conductor, or you have a violation. It really is that simple. So these 8 gauge wires are protected by a 150 amp overcurrent device upstream, and they terminate at a 50 amp overcurrent device downstream. That might meet the tap rules, and if it does, then we're okay. So getting into the actual requirements, and then we'll tie all of this together. We go to section 240.21, which says location in circuit. It says conductors must have ground fault and short circuit and overload protection at the beginning of the circuit unless allowed in A through H. Okay, almost every circuit that we install meets that criteria. Most of the time when you put in a circuit breaker or fuse, it provides ground fault and short circuit and overload, and we're done. Take a bathroom, for example. If I have a bathroom and I plug 6 curling irons and a hairdryer in at the same time, that's an overload, the 20 amp breaker trips. If I were to take one of those cords and cut them with the scissors, that would be a short circuit and the breaker trips. If internally, maybe the black conductor contacted the metal object inside of the hairdryer or something, that would be a ground fault and the 20 amp breaker would trip. So normally, we have one overcurrent device and it provides protection against everything. But that's not always the case. We don't do that with motors, we don't do it with air conditioners, and we don't do it with feeder taps. Now, before we get into the rules, the first thing here, 240.21 says conductors that are protected in a way described in A through H must not supply another conductor unless it's protected in accordance with 240.4. Now, that's a mouthful, and the first time you read it, you really have to push pause and figure out what you just read. All this is saying is, look, these feeders on the left are not protected in a way described in A through H. So you can tap the feeder conductors. These feeder taps, however, may not be tapped. So I could create as many taps off of these 1-aught conductors as I wanted. I could tap these things 100 times if I wanted to. What you cannot do is tap from a tap conductor. So these 8 gauge wires that go down to a 50 amp fuse or breaker, I could not tap the 8 gauge wire and then go down to maybe a 30 amp fuse or breaker. You could tap the 1/0 and do that, but you cannot tap the tap conductor and do it. So feeders can be tapped as many times as you want. Taps cannot be tapped at all. All right, so here's what the rule says, and you'll notice a little bit of change here in the 2020 code in the underlined yellow text, but I'll be perfectly honest, it didn't change anything technically, it's just a clarification. So feeders can be tapped at any point on the load side of their overcurrent device in accordance with 1 through 5, but they may not use the allowance of 240.4b, which is the next higher rated device. Okay, I've got a 125 amp circuit breaker. Coming out of a 125 amp circuit breaker, just in a normal general condition, I could have 2 gauge, which is rated 115 amps. Now, that may seem weird that you can put a 115 amp wire on a 125 amp breaker, but it's fine, and that's because of the next size up allowance in section 240.4b. You see, there's no such thing as a 115 amp breaker or fuse. Well, I shouldn't say there's no such thing. Hey, for all I know, somebody's invented it. But the code doesn't recognize it. The code in table 240.6a gives us a list of what the code considers standard ratings of devices. So you look at the ampacity of the conductor, you say, man, I got a 112 amp load. What size wire do I need? You scroll down table 310.16 and 75 degree column because you're over 100 amps. And you realize that you need a 2 gauge conductor. So you say, okay, cool, I got 115 amp ampacity, I need to go get me a 115 amp breaker or fuse, and I'm good to go. You go to the supply house, and you realize there is no 115 amp fuse or breaker. So what is a person to do? Well, you use the next size up, and that would be 125 amps. Now, you can do that for the feeder. You cannot do that for a tap conductor. Tap conductors do not get to use the next size up allowance. So for a tap conductor, if this was the load side of a tap, maybe I've got a 400 amp circuit breaker with 500 kc mil, and then I tie on a 1 gauge conductor to supply this 125 amp breaker. That would be a tap, and I'm not allowed to use the next size up rule for a tap. I would have to go back to my table and find a legitimate 125 amp wire, and that would be 1 gauge on the 75 degree column of table 310.16. So I cannot use the next size up allowance. The clarification that they made in the 2020, when we think of tap conductors, I think most of us think of this. You've got a feeder conductor, and it creates multiple small wires. And indeed, that could be a tap. But do you remember the definition? A tap conductor is simply a wire that doesn't comply with the regular overcurrent protection rules, but does comply with the tap rules. So what this section is trying to clarify is I've got a 400 amp breaker in this switchboard. Now, I didn't put it there, it's just happening, it's an existing building. I walk up and there's this beautiful 400 amp circuit breaker sitting there, nothing coming out of it, so why buy a new breaker? I'm going to go ahead and use it. But I'm only supplying a 200 amp load and a 200 amp panel. Could I come right off of the lugs of this 400 amp breaker and start my tap immediately with 3/0 copper conductors? The answer is yes. I could come out of here with 3/0 going right from a 400 amp breaker as long as they meet the tap rules. So maybe they remain outdoors and they supply a 200 amp main breaker panel. As we're going to find out in a minute, that would be perfectly legal. So tap conductors can start immediately at the overcurrent device, and that's always been an allowance. It was just a clarification in the 2020 saying that feeders can be tapped again at any point on the load side of their overcurrent device. All right, let's get into the rules. This is so much easier than you might think. Tap conductors up to 10 feet, and that's probably our most common tap conductor. These taps are allowed if, item 1A, if the ampacity of the taps carries the load. Well, that's always required. Every wire has to carry the load. That's never an option. So complying with 1A is almost automatic. Your wires always have to be carried, they always have to be sized to carry the load. So that's simple enough. Item B is really the crux of the rule. The ampacity of the taps is not less than the rating of the overcurrent device that they terminate to. That's the key. So I've got 150 amp fuses protecting 150 amp wire, and then I tap some conductors off of it. I got some 50 amp fuse disconnects here. I've got one 50 amp fuse disconnect and then another 50 amp fuse disconnect. I could come off with 6 gauge wire that's rated 55 amps at 75 degrees C if my terminals are rated 75. If they're not, I would have to use 8 gauge, which is rated 50 amps at 60 degrees. But here's the key. I size the taps based on the overcurrent device that they terminate to on the load side. Now, why is that legal? How is it okay to have a 6 gauge wire protected by a 150 amp circuit breaker or fuse? Well, here's the reason. Do I have ground fault, short circuit, and overload protection? If I take those black and red conductors and smack them together, that would be a short circuit. Am I going to generate enough fault current to open a 150 amp device? Absolutely. Remember earlier I said it's going to pull thousands of amps of current, so a short circuit is going to open the 150 amp breaker. What about a ground fault? What if I take the red wire here and there's some sort of a fault and it hits up against the metal parts of the wireway? Is that going to open the 150 amp breaker or fuse? Absolutely, no problem. It's going to generate thousands of amps of current. So we have ground fault and we have short circuit protection. What about ground fault? What about overload protection though? What if somebody starts pulling more than 50 amps of load on this circuit? What keeps these wires from melting? Well, the fuse that they terminate to keeps them from melting. Remember, it cannot terminate main lug. It has to terminate main breaker or a set of fuses rated not higher than the ampacity of the conductors. Before these conductors melt, the fuses or circuit breakers would open. So we're providing overload protection at the end of the circuit, ground fault and short circuit protection at the start of the circuit. And that's why tap conductors are located in section 240.21, because 240.21 says you have to provide ground fault, short circuit, and overload at the start unless allowed in A through H. We're here in subsection B, which is tap conductors, and that's how they work. Ground fault and short circuit protection upstream, overload protection downstream. Number 2, the tap conductors must not extend beyond the equipment they supply. That's easy enough. I mean, it has to go to a breaker or fuse, so where else is it going to go? You know, just don't let it go all over the place. Number 3, and they're only 10 feet long anyway. Number 3, they have to be in a raceway. Kind of strange that they can't be in like MC cable, but it is what it is. They have to be in a raceway. And then number 4, the ampacity of the tap conductors must not be less than 1/10 of the rating of the upstream overcurrent device. Our upstream overcurrent device was a 150 amp breaker. So that means the smallest ampacity that I could use for a tap would be 15 amps. So could I tap 14 gauge here and go to a 15 amp circuit breaker? Absolutely, that would be okay. But if this upstream was a 200 amp circuit breaker or fuse, could I still tap 14 gauge and come down to a 15 amp overcurrent device? No, I could not. I would have to use 20 amp conductor because it must not be less than 1/10 the rating of the upstream device. I told you guys I was going to tell you a story of where I used it. A friend of mine called me up a few years ago and he said, hey, I need you to do some electrical work at my house, but don't worry, it'll be easy. And I'm like, yeah, great, of course, because you know how easy it's going to be. So I get over there and he bought an RV. And he said, well, I need a receptacle, a 120 volt 30 amp receptacle on my driveway to plug in my RV, but here's why I think it's going to be easy. My panel is right here at the driveway, and he's got a panel board on the outside of the house, which is common in some parts of the country. So I'm looking at it thinking, okay, this actually might be easy. You're right. So I open up the panel and my heart sinks because all it is just a 200 amp breaker with 200 amp wire feeding a 200 amp panel on the other side of the house. This is not going to be easy. He does not have any real good way of getting a 30 amp circuit to his driveway. And then I remembered the tap rule. So I decided to go to the store and I got some lugs. It was 4/0 aluminum coming out of the 200 amp breaker. I got a termination device like a Polaris that was rated for both copper and aluminum. I I I stripped some of the 4/0 aluminum, tied onto it, and then took a 10 gauge wire out of it and went where? Did I go straight to the receptacle? No, I went to a 30 amp fuse disconnect. And then out of that 30 amp fuse disconnect, I added the receptacle. Now, that was more work than I wanted to do, but compared to getting to the other side of the house and having to pull a 10 gauge home run all the way back across the house, it was a lot easier. And really, the hardest thing about this for me was simply remembering the fact that that was an option. Once I remembered the tap rules, I was in the clear. It was easy as could be. There is an exception to how I size 10-foot taps. It says if listed equipment like a surge protection device has specific instructions for conductor sizing, then the conductor can be sized based on the instructions. I'm not a huge fan of this language, listed equipment. I mean, listed equipment could be anything, any equipment that's listed, but it says like a surge protective device. And what I think they're trying to say is something that has no real load to it. Like a surge protective device doesn't have a load. So do I really need overload protection for a surge protection device conductor since there's not really a load on it? So if it's a no load piece of equipment and it has specific instructions for conductor sizing, then go ahead and just follow the instructions and don't worry about it. So we talk about 10-foot taps, and they're actually pretty easy. 25-foot taps follow pretty much the same rule. For a 10 to 25-foot tap, number one, they have to have an ampacity of at least 1/3 of the upstream overcurrent device, and we'll talk about that. Number two, they have to terminate to a single overcurrent device rated not greater than the tap ampacity, and then number three, they have to be in a raceway. Okay, well, number three, simple. Just put them in a pipe and you're done, right? Or a wireway like this is considered a raceway. Number two is simple. They have to terminate to a breaker or fuse that provides overload protection that's not rated higher than the rating of the tap conductor. And then number one is a little bit trickier. They have to have an ampacity of at least 1/3 the rating of the upstream overcurrent device. Over here on the left, I have a 400 amp circuit breaker. It supplies 500 kc mil. That's a regular feeder. That's not a tap. I come down here and I add some terminals, and I've got a 225 amp main breaker panel, and I've got a 100 amp fuse disconnect. I want to supply both of those. So for my 225 amp main breaker panel, I just need a 225 amp wire, and that would be 4/0 copper rated 230 amps. So that's easy enough. Tie some 4/0 and you're good. For the 100 amp feeder circuit though, it's a little bit more complicated. The first thing I would do is I'd find a 100 amp conductor, and that's going to be, I think, 3 gauge is rated 100 amps. But the problem is I also have to figure out the 1/3 of the upstream device. So 400 amps divided by 3 is 133 amps. So my tap conductors have to be rated at least 133 amps. So I would use a 1/0, which is rated 150 amps. Now it's just the rating of the wire. Can these still land on a 100 amp fuse disconnect? Yeah, no problem. No problem at all. It's just that the wires have to be a little bit bigger. And the reason for that is, let's think about it. Going longer than 10 feet, going from 10 to 25 feet, I've added more resistance. We do have to remember that at a certain point it would get crazy enough that I would lose my ground fault and short circuit protection. Could I tap, for example, could I tap 14 gauge wire off of this 400 amp breaker and run it 100 feet? Well, no, because by the time you get 100 feet of 14 gauge wire, if you touch them together and try to trip a 400 amp breaker, it might not happen. You might not generate enough current to actually initiate that overcurrent device. So the longer we get, the more restrictive the rules get. So I'm limited to 1/3 the rating for a 25-foot tap, whereas on a 10-foot tap, I only have to worry about 10% of the rating of the upstream device. Where it gets really strange is outdoor taps of unlimited length. This is pretty much the wild, wild west. Do whatever you want, and you're going to be okay on outside taps of unlimited length. So unlimited length tap conductors that remain outdoors are allowed if, number one, they have to be protected from physical damage. Well, yeah, you're not just going to lay them on the dirt, so that's easy enough. Number two, just like our other taps, they have to terminate at a circuit breaker or a set of fuses rated not more than the tap conductor's ampacity. So if I've got some 400 amp tap conductors, then they have to terminate to a 400 amp fuse disconnect or a 400 amp circuit breaker, just like the other taps. Number three, the overcurrent device for the tap conductors, the downstream side, has to be part of or near a disconnecting means. Well, yeah, I mean, they're going to land at a breaker or a fuse, so more than likely it's going to be a disconnecting means whether we like it or not, to be honest. Number four, the disconnecting means for the tap conductors has to be readily accessible. That's always required. And it has to be outside. Well, yeah, it's an outside rule, so yeah, it has to be outside. Or it could be inside nearest the point of entrance. Let's say I'm supplying going back to my buddy's house. I have that 200 amp breaker. Could I tie some lugs onto it with some 10 gauge wire and go 100 feet over to his detached garage, hang a 30 amp fuse disconnect on the outside and be good? Yes. Or they could even go into the garage as long as that disconnect is immediately at the point of entrance. Either way is okay. But the funny thing about the outdoor tap conductors is there is no length limitation. I really could take those 10 gauge wires and run them 100 feet or 1,000 feet to a detached garage and we would be okay. It's rather surprising. No question we have overload protection on those. They terminate to a 30 amp breaker or fuse. But do we really have ground fault and short circuit protection if I run 1,000 feet of 10 gauge wire and put them on a 200 amp breaker? It's debatable. But here's the thing, this has been in the code for a very long time, and I've never heard of any documented incidents of where this was a problem. Now, we allow this outdoors for another reason, and that is if something did go wrong, if there was a fire or something, it's outdoors. You're not going to burn a building down because the wires remained outdoors. So very, very lenient allowance here for unlimited length outdoor tap conductors. With that said, that's pretty much all there is for feeder taps. They're really not that bad. Again, once you understand the concept, ground fault and short circuit protection upstream, overload protection downstream. It's just like a motor or it's just like an air conditioner. It's treated the exact same thing, the exact same way. All right, I hope you got something out of the video. If you're interested in books or PowerPoints, go to my website, ryanjacksonelectrical.com/shop, and you can check out books and PowerPoints and things if you're an instructor. Follow me on Instagram. I just started doing Instagram like 2 days ago, so there's nothing there yet, but I've been doing a little bit of stuff, so Ryan_Jackson_electrical. Follow me on Facebook, Ryan Jackson Electrical Training, or YouTube, search for Ryan Jackson Electrical. You can also email me if you ever have questions, ryanjackson618@gmail.com. And with that said, thank you very much for joining me. I hope you guys have a great day. Thanks.